Welcome to Communication Networks 2. My name is Javier Acevedo, and today we are going to have together an introduction to software-defined radios. The table of contents that we are going to tackle together is the following. We are going to start with an introduction in which we are going to see what is the role of SDR technology in 5G, in the development of 5G networks. Then what we are going to have is an overview about the basics about signal processing. We are also going to review the fundamentals about digital communication systems. Then we are going to proceed studying together the fundamentals and definitions of software-defined radios. We are going to see what are the hardware architectures that compose those devices, and we are going to see what are the software environments that normally are used for programming the SDRs. Finally, we are going to have an overview of the applications that we can develop by using SDRs. Here in this slide, what we can see is the 5G atom. The 5G atom has many enabling technologies, and one of those technologies are SDRs, or software-defined radios. And now the question is, how can SDRs be applied in the development of 5G networks? Here in the right side, what we have is a radio communication system that normally is used as a global positioning system, or GPS. When we develop a new communication system or test bed, basically we have to assume huge risk because we establish an specification that can have variations during the development phase. So new changes or redesign have to be introduced during the development phase. However, if the functionality of our communication system is implemented only on hardware, basically when a change arises, we have to change the whole communication system. And this implies huge cost and also implies huge amount of time because you have to fabricate a new communication system. The approach of SDR is to implement the communications protocols directly on software instead of on hardware. By doing so, when we have a change or when a redesign is required, by updating the software firmware, what we can obtain is a new functionality directly in our device. Then we can really save a lot of time and money by introducing those changes rapidly by software. Now, what we are going to do is to have a quick overview about the basics of signal processing. Let's going to start with the basic properties of periodical oscillating sine wave. A periodical or any periodically oscillating sine wave has three fundamental properties. First, what we have is the amplitude. Second, it also has a frequency, a defined frequency, and a phase. If we want to formulate this into mathematics, or we want to provide a mathematical formulation to describe those two properties, which is also known as the waveform, we have that the sine wave is the multiplication of the amplitude by a mathematical sine function that has an omega frequency and a phase phi. Other two really important properties of a signal are its velocity and its wavelength. Let's go to study deeper those properties. Let's go to start with the amplitude. The amplitude is the measurement of the level of voltage or energy with respect to a specific reference. Here in this picture, what we have is that our reference is the horizontal axis. Then the displacement, the maximum displacement of our signal respects to the horizontal axis, what it's going to provide to us is the amplitude. This is the measurement of the amplitude of the signal. Another property is the frequency. Here in the picture, what we have is that we have two different signals, or they are the same signal, but they have two different frequencies. The frequency in the blue signal has a higher frequency in comparison to the signal in the red line, which has a lower frequency. The frequency represents the number of cycles per unit time, and the relationship between the frequency and the time is defined as f. The frequency is equal to the inverse of the period. The phase represents the angular shift between two sine waves, which can be measured in radians or degrees. Here we have two identical sine waves that are differentiated only by the angular shift that they have. The red signal here has a phase of 0, while the other orange signal has a right shift of 90 degrees. The wavelength represents the spatial period of a wave, which is the distance over which the wave is repeated. In our slide, we have that our wavelength is the distance between two crests, or what is the same is the distance between two throws. So every two crests our signal is repeated, and this is what is called wavelength. If we want, by knowing all those four properties, or we can really establish what is the velocity of our propagating signal. The velocity of a propagating signal is the product of the frequency by the wavelength, or what is the same, we can rearrange mathematically the previous formula to establish what is the frequency of a signal by knowing its velocity and its wavelength. We can also calculate what is the wavelength by knowing the velocity and the frequency. We must recall that the units in the international system of velocity are given in meters per second, the frequency is given in hertz, and the wavelength is given in meters. There are two main domains or representation of a signal when it's propagating in a medium: the time and the frequency domains. As we can see in the picture right here, we know that the time and the frequency domain are perpendicular. And if we want to go from the time domain to the frequency domain, or vice versa, from the frequency domain to the time domain, what we need to use is what is called the Fourier transform, which provides a mathematical relationship between this signal representation. As an example, let's go to evaluate, or let's go to review the Gibbs phenomenon. If we have different signals with different amplitudes, different frequencies, and different phases, and we sum up all these signals together, what we are going to have is approximately a square wave. And this square wave, if we want to analyze this square wave in the frequency domain, what we are going to obtain is that the spectrum of that frequency is going to be the sum of the single individual contributions in frequency of every composing signal, a sine signal that compose the square wave. In this, as we can see here, it's really easy to go from one domain to the other, or to analyze one signal from one domain to the other by using this Fourier transform. Another important fact to consider when we are analyzing the periodical signals are the sampling and the quantization. Here, what we have is an analog signal that is continuous in time, and this signal can be converted into a digital signal which is decreasing time through a sampling and quantization. The sampling is the conversion of the continuous signals in time into discrete signals by taking samples of the continuous signal at discrete times. So we have this continuous signal in time, and by taking samples of the signals, we can discretize that continuous signal. Then what we require is a conversion of the sample signal into a digital format through the quantization. And when we discrete a signal and we want to reconstruct the signal back, we have to consider a criterion that is known as the Nyquist theorem. And this theorem established that in order to reconstruct a time-discrete signal into a continuous time signal without losing any information, it is necessary that the sampling satisfies the following criterion. The sampling frequency has to be at least twice the frequency of the signal. Let's going to proceed by reviewing some fundamentals about digital communication systems. Let's going to assume that we want to transfer digitally this image using wireless medium. So basically what we have to do is to transform the image into bits. Then these bits are going to pass through a phase that is going to be called the source coding, that is going to provide us another bit as an output. Then we have to do the channel coding for the modulation, and then we have to go through the radio frequency front end until we obtain the up conversion, in which we can really transfer the signal. Then we down converted that signal until from the analog, we down convert the analog signal back into bits until we obtain our image back at the receiver part. Let's go into the details about these transmissions and reception of data. Here what we have is the same graphic that we just presented. So a digital communication system is the collection of digital and analog processes to handle the processing and manipulation of binary information. as we can see in the picture right here, there are two main domains. The analog domain that is represented by the radio frequency front end, and the digital domain that is basically represented by the digital source, the source encoding, channel encoding, digital modulation, and the conversion from digital to analog or analog to digital. The main goal that we have with those digital communication systems is the transmission and reception of data, which propagate into an electromagnetic medium. And as in this point, it's important to remember that electromagnetic waves, are the waves in which the information is traveled, can be represented in terms of sine waves. And that was the reason to evaluate the properties of the signals previously. And every digital transceiver is the receiver and transmitter, is composed of several functional blocks to map electromagnetic waveforms to bits during the modulation and demodulation operations. However, as we can see here, when the electromagnetic waves are traveling, there are many challenges to be considered when we are designing our digital communication system. One of them is the noise, the other is the interference, and another is the poor signal. So in order to quantify how good is our medium to propagate a signal, we have what is called the signal to noise ratio. That is going to give us a measurement of how good our medium is to transmit a signal. Let's going to evaluate the function, or let's going to review the function of every building block of a communication system. So we have the data sources, as we have seen, can be the images or voice or any data that we can transform into a bit stream. And what we have to do in the data source is to generate or receive the binary representation of the real world. It can be speech, it can be videos, it can be music, it can be images. Then we have to go into a source encoder. The source encoder, what it's going to do is to remove the redundancy from the transmit data stream, and then what it's going to do is to reintroduce this redundancy in the receiver side. In the channel decoder, as we are going to transmit our data into a lossy electromagnetic medium, basically what we have to do is to put more redundancy to control errors during the transmission of the data. And then in the symbol modulation, what we have to do is to map the bits at the transmitter into a carrier signal that is going to be in charge of traveling into the medium. And finally, in order to achieve that this signal travels into the medium, we have to do a conversion from the discrete time samples into an analog waveform, and vice versa in the transmitter side. Finally, if our radio frequency front end, we prepare the analog waveforms for transmission at the radio frequencies, and when we receive the signals, basically the radio frequency front end, what it does is to convert the received radio frequency signals to an analog baseband signal. What it means is that what we are going to do is to remove the carrier signal that we have employed to transmit this signal in the electromagnetic medium. There are some modulation schemes That is a way in which we are going to transmit our data. And as you can see from the picture, there are four main modulation schemes. The analog modulation, there can be an modulation in amplitude or AM, a modulation in frequency or FM, and a modulation in phase that we are going to call phase modulation or PM. The digital modulation can be of two different classes, the single carrier modulation or the multi-carrier modulation. In the single carrier modulations, we have the amplitude shift keying or ASK, the frequency shift keying or FSK, the phase shift keying or PSK. On the other hand, in the multi-carrier modulation, we have the QAM or OFDM, the orthogonal amplitude modulation or the orthogonal frequency division multiplexing that has been vastly employed in the development of 4G networks. Finally, we have the pulse modulation and the spread spectrum. Now, what we are going to see is to review how these digital modulation schemes work. So here, what we have is our bit stream, and it's composed by 1, 0, 1, 0. Here, down here, what we have is our high frequency carrier signal. If we want to do an amplitude modulation in amplitude, basically what we are going to do is to assign the higher amplitude to the ones and the lower amplitudes to the zeros. So in amplitude, what we can modulate information by assigning the bit 1 as a higher amplitude and the bit 0 as a lower amplitude. It happens the same in frequency. In frequency, the higher frequencies are going to be represented as the 1 and the lower frequencies are going to be represented as zeros. And finally, the changes in phases are going to be represented. The 1 is going to have one phase and the 0 is going to be represented as another phase. So as we have a bit stream for 1, 0, 1, 0, we have three different changes. Here we have a phase shift. Here we have another phase shift, and finally here we have another phase shift. Now we are going to continue with the fundamentals about software-defined radios.